Hello, we're going to talk about some non-experimental research designs for quantitative studies today. This is chapter 7, and just going to go over 4 different types. I know the chapter talks about surveys a little too, but I think that's a little easier to digest on your own. So first one is descriptive studies. And these are statistical studies that describe some phenomenon. They may include averages, the median, frequency. You might think that these would not be very valuable in statistical research, but they're actually very nice for creating a snapshot of what the existing condition is. For example, let's say you want to study some kind of technique that's used with visually impaired students. And before you start, you might want to know, well, what's being used already? And it's very helpful to say, oh, well, 50% of elementary schools use this one technique with visually impaired students, and so on. So it can be very helpful for the beginning portion of research. And actually, one of my, probably my most impactful publication was this report called Why Rural Matters, which is simply a descriptive study. We looked at some public data on all the statistics for rural education across the country, and then created a page for each state, so you can see this on the right, and then some maps on different educational outcomes, policy context, socioeconomic challenges, things like that. But it was all just descriptive. We didn't make any inferences, didn't go too deep into why this is the situation or what should be done about it. Of course, we do make some recommendations, but the purpose of the report is basically just to say, hey, this is what rural education looks like in these different states. And when you're evaluating them, you should make sure that if something did use descriptive statistics, that they didn't go too deep into, well, this is because A causes B. You really can't tell that from a descriptive study. And I'm going to put this here. In any study, really, you should describe the participants and instruments, the sampling strategies. You should describe all of that completely. So I won't keep going over that, but I did want to point that out as you're reading these studies. The next type is comparative studies, and here we're just looking at 2 categories. It really could be 3 or more. I think your book mentioned 2, but different categories on some variable. For example, we may look at males and females on test scores, or salaries, or time focused on a task. Is there a difference in how males and how females do? Now, it's very important that it's not necessarily the gender that's causing the outcome. We're not saying that participation in one group is the reason why the outcome is significantly different. We're just looking for, is there even a significant difference? And this is in contrast with correlational studies, where we're looking at 2 continuous variables and a relationship between them: height and weight, time spent learning the material versus performance on the outcome or the test, whatever it is. Real quick, simple diagram here showing the difference. Comparative, we have guys and girls. I think these are both singing groups, maybe. I just Googled them. I really don't know. But maybe we're going to look at their tone quality. Is there a difference between guy singers and girl singers? So that gender, that guy or girl, would be our independent variable, and it would be a nominal variable or categorical variable. Versus if we're looking at elevation and mean annual temperature in Nevada, here we're looking at two different continuous variables. Elevation could take on any of these values in between 0 and 2500. Mean annual temperature could take on any of these values. And something to mention is that you can use correlational studies when you have two continuous variables. And really, you can even use it when you have categorical independent variable to predict an outcome, but it's not showing the cause. We're just trying to make a prediction. If we have this value on the independent variable or variables, what is our best guess at the value on the dependent variable? It's not necessarily that these independent variables are causing that dependent variable, and it certainly won't predict it exactly, especially when we're predicting a single individual's outcome. There's a lot of range of variance of what that actual value could be, but it does give us a helpful prediction for whether or not a student will succeed in their freshman year of college. Admission committees use this kind of predictive study. Medical researchers use this based on what we know about this patient. What is our best prediction for how long they will live when they have this certain diagnosis? So actually, let me go straight into an example here. So this is a simple regression example. This is an equation, don't be scared off. And you may remember back from algebra days where we had y equals mx plus b. This is very similar. Notice this is in the opposite order on the right side, but that doesn't matter. Whatever is attached to the independent variable there is our slope, we can call it, in simple regression. And whatever is not attached to the x, or to whatever the independent variable is our y-intercept. Now here's something different. We have a little hat or a caret on top of our y, on top of our dependent variable. This means we're making a prediction. So this will not be an actual data point. This will be a predicted data point. Versus this x will be an actual data point. Or we can plug in our own data point, but this is an actual and this is a prediction. Now you might think, well, if we have the actual x's and the actual y's, why don't we just use the actual y? Well, we do when we're creating this equation. So this regression equation is what's called a line of best fit. When we create a scatter plot of all the different data points, like we had, let's see, right here, notice that scatter point. Each one of those dots is based on an actual x and an actual y. Then there's a line, you don't see it here, but you can kind of picture a line going through those that fits well. And that's the line of best fit. So that's the equation of the line of best fit. And let's go on and try an actual example. Let's say we're going to predict your final exam score in this class. And of course, we don't have a final exam, but from number of hours of studying. We somehow need to get some actual data first. Now this may be previous year's tests, it may be test scores from a similar class, we may just get lots of tests across the campus, and for everyone we have a student, how many hours they studied, and what their final exam score was. That's their x and their y. We plot all those points on the graph, get the line of best fit, and that gives us a regression equation. Let's say that our regression equation gives us an a value of 30 and a b value of 5. In other words, if x is 0, if you don't study for the exam at all, 0 times b is 0, so your predicted score is just your a, which is this 30. In other words, If you don't study for an exam at all, we're going to predict you get a 30%. Of course, there's a lot of variance there, and that's why I caution in using it for an individual prediction, but it's our best guess based on our data. Now, let's say that you study 10 hours for the final. What would we predict your grade as? Well, A is still 30. Our X right here is going to be 10 because we've studied 10 hours, and this student has studied 10 hours. And B is 5, so 10 times 5 is 50, plus 30 is 80. We'll predict 80% for this student. Now, really, we should have a confidence interval around it, but again, this is our best point estimate of the exam score. Okay, and these values, again, 30 is what we predict if the person has no X, so in other words, no hours studying, and B is for every extra hour that you study, we predict that your percentage on the final will go up by 5%. That's what the slope means in this case. Now, multiple regression is very similar to simple regression, except we have more than one predictor. And in college admission, for example, we might look at SAT scores, we may look at high school grade point average, high school rank. We may look at several factors and then create a single predicted value that we think you would get on college freshman GPA. And maybe our admission, we want you to have a predicted value of 2.5 or higher, or we're not even going to admit you unless there's special circumstances. So multiple regression just has more than one predictor. An equation might look like this. Notice here I don't have an A, I have a B0. This tends to be a little more common, but it shows up a lot, so I'm trying to show you different ways it'll show up. X1 is just our value of whatever our first predictor variable is, so maybe hours studied for the final, should have had an S there. And X2 is socioeconomic status, so how wealthy your family background is. Now you might think, why in the world would I suddenly throw that in for an exam score? Because people usually don't have control over this, and isn't this prejudiced? However, remember, we're not saying that this causes this exam score. We're just saying that this is a very helpful predictor for better or worse. And in this case, socioeconomic status usually is the #1 best predictor in educational studies. And I would certainly say that's for worse, not for better, but it is. It is what it is. And then part of our job as researchers is to decide, why is that? What about a low socioeconomic status is causing these low exam scores, and how can we change that? How can we make it so that wealth does not influence educational outcomes? But that's much deeper than we can cover right here. Let me jump on. Logistic regression is similar to simple and multiple. The only thing is the outcome variable here is one of two categories. In medical studies, it's often die or does not die. It may be success, fail, entrance into college, rejection of admission into college. And final thing I want to cover is statistical versus practical. Even if, and this is anything, not just correlations, even if we say that a p-value is less than 0.05, that doesn't necessarily mean much. It could just be because of a high sample size. A high sample size will always make your statistical significance higher. In other words, it'll make your p-value lower. Practical significance is, does it really matter? And this could be either, is the effect size actually big enough that it would make a difference? Or it could mean, are these variables even important? Is it important that toenail size is slightly bigger? But there's a big difference between a p-value and an effect size. And an effect size typically is what's more important. There are ways to look at causal effect using correlation, but they're very sophisticated, and it's not just pure correlation. And finally, ex post facto is dealing with existing